Everyone, welcome to The Explainer. Today, we're taking a journey deep inside the invisible, high-energy world of nuclear physics. We're going to demystify the complex mechanics of what actually happens inside a nuclear reactor. And we're doing this by tracking the journey of a single neutron, proving that what sounds like intimidating, overwhelming science actually follows a really beautiful, logical set of rules. Picture the environment inside a nuclear reactor for a second. It's kind of hard to wrap your head around, right? It's just pure, invisible chaos. You have billions of microscopic particles flying around, colliding, absorbing, and reacting every single microsecond. The question we really have to ask ourselves is, how in the world do we make sense of these invisible collisions? How do we calculate, predict, and ultimately control a chaotic storm of flying neutrons? So, to make sense of all this, we're going to follow a pretty straightforward roadmap today. We'll start with the rules of collision, move on to the probability of interaction, look at calculating reaction rates, and finally, wrap up with the radiative capture process.
All right, part one, the rules of collision and finding the right energy. Let's get right into it.
Okay, so what actually happens when a collision goes down? Well, in a reactor, neutrons don't usually just bounce off a target like a pinball. They get completely swallowed up. And when that happens, we get what's called a compound nucleus, or CN. This is a brand new, highly unstable, and temporary nucleus that has essentially eaten our incoming neutron, along with all the kinetic energy it brought with it.
Think of it like a before and after, because this is absolutely crucial. Before the hit, you've got this unexcited nucleus. Everyone's chill, sitting exactly where they're supposed to in their normal energy shells. But bam, the neutron hits, gets absorbed, and suddenly this nucleus is highly excited. It is seriously agitated. It's carrying all this excess energy from the impact, and it has an immense appetite to just get rid of that chaotic energy as fast as possible.
But here's the catch. Target nuclides are surprisingly picky. They won't just absorb any random neutron that flies by. It operates on a strict lock-and-key mechanism. A reaction is really only going to happen if the incoming neutron has the exact, specific energy level that the nucleus is looking for. When it's a perfect match, the probability of a reaction just skyrockets. In reactor physics, we call these massive peaks resonances.
Which brings us to part two, the probability of interaction, hitting the target.
So we know neutrons need specific energies to react, but how do we actually measure the odds of hitting that perfect target in a massive sea of atoms? We use something called a cross-section. Now, don't let the technical term fool you. While it's mathematically about probability, the easiest way to visualize a cross-section is simply as a target size. It's the effective area the target shows to the incoming neutron. And the wildest part? That target size literally changes depending on how fast the neutron is moving. Just picture a whole beam of neutrons rushing toward a solid cube of target material. If we look at the density of the incoming neutrons, the density of the target atoms, and the speed those projectiles are traveling, we can figure out exactly how many neutrons are going to crash into those targets every single second.
Now, since we're talking about subatomic scales here, this cross-section area is unfathomably tiny. We're talking 10 to the power of negative 24 square centimeters. That number is so small that physicists decided to give it a slightly more relatable name. They literally call it a barn. Yeah, as in the old joke that a terrible shot couldn't hit the broadside of a barn. Well, for a neutron with just the right energy, this impossibly microscopic area is absolutely the broadside of a barn.
All right, part three, calculating reaction rates, or measuring the chaos. Bringing math into the picture can seem daunting, but it's actually super intuitive once you break it down.
Let's ground ourselves with this strict definition for a second. The reaction rate is simply the number of reactions taking place per unit volume of the target nuclide medium per second. That is the core of what a reactor physicist wants to know. They're just asking, how many times is the magic happening in this specific little box of material every single second?
And what looks like a terrifying formula is really just a simple 4-ingredient recipe. To find the total reaction rate, you just multiply 4 things. N, the number of targets you have, N, the amount of neutron bullets you're firing, V, how fast those bullets are moving, and finally sigma X, that microscopic cross-section, which is the probability target size we just talked about. Targets, bullets, speed, and probability. Multiply them all together, and boom, you've mapped the chaos.
To make life even easier, reactor physicists like to group these variables. If you combine the neutron density and their speed, you get neutron flux, literally the volume of neutrons crossing an area per second. Combine the microscopic cross-section with the target density, and you get the macroscopic cross-section, the overall probability of a reaction happening across a physical stretch of material.
These are, hands down, the two most critical macro measurements used to actually run a nuclear reactor.
Okay, final stretch. Part 4, the radiative capture process, the ultimate collision. We know the rules, the math, and the probabilities. Let's see it in action.
So here's the deal with most reactor energy ranges. When a collision happens, it goes straight into that compound nucleus mode we discussed. And in certain reactions, known as capture reactions, the target doesn't give the neutron back. It doesn't bounce off, it isn't spat out later. The neutron is permanently swallowed up by the target nucleus.
Let's track exactly how this radiative capture plays out chronologically. Step 1. Our neutron smashes into a nucleus that has a specific mass. Let's call it A. Step 2. The neutron is absorbed, creating that highly agitated compound nucleus. Because it ate a neutron, its mass is now A+1. Step 3. It absolutely has to calm down and de-excite to reach its ground state. But instead of ejecting a particle, it just releases a burst of pure energy in the form of a gamma ray.
When you put that whole sequence together, it's pretty amazing. You start with the reactants, the tiny neutron and the target nucleus. They merge into that highly agitated state in the middle. And then finally, they settle into a brand new, heavier, stable isotope, shooting off a gamma ray in the process. It's literally radiative capture happening right from start to finish.
But before we wrap up this explainer, I want to leave you with a bit of a mind bender. We learned today that these reaction probabilities, these microscopic cross-sections, shift drastically with every tiny change in energy, right? And they completely vary from nuclide to nuclide. So how in the world do scientists keep track of the data for every single stable and unstable nuclide out there? Well, the answer lies in something called evaluated nuclear data files. It's this massive, ongoing, international effort to literally map the physical universe. But how they actually build and distribute those databases, that is definitely a fascinating story for another time. Thanks so much for joining me on this journey into reactor physics. Keep wondering, and I'll catch you on the next explainer.